Hello, in this project I investigate whether machine learning applied to Sentinel-1 synthetic aperture radar imagery can distinguish sea ice regimes associated with ice arch and no ice arch conditions in the Nares Strait. The Nares Strait is a narrow Arctic gateway located between Greenland and Ellesmere Island, and it plays an important role in controlling the export of Arctic sea ice from the Lincoln Sea into Baffin Bay. During winter, stable ice arches can form within the strait, creating consolidated and mechanically rigid ice conditions. In contrast, during summer or no-arch conditions, the sea ice becomes far more mobile, fragmented, and dynamically active. Understanding these sea ice regimes is important because they influence Arctic freshwater export, sea ice transport, ocean circulation, and broader climate processes. However, the Nares Strait is narrow and dynamically complex, meaning traditional low-resolution sea ice products often struggle to capture these small-scale features. To address this, I use Sentinel-1 SAR imagery because it provides high-resolution all-weather, day and night observations of the Arctic surface. I then combine this Earth observation data with machine learning methods including k-means clustering and random forest classification to investigate whether physically different sea ice states produce measurably different SAR texture signatures. The project combines remote sensing, patch-based texture analysis, unsupervised and supervised learning, spatial rollout mapping, and sea ice drift retrieval to explore how AI methods can be applied to the Arctic cryosphere research. In the rest of the video, I will walk you through the code for my project. The project uses the imagery over the Nares Strait to classify the textures. The code is structured into several main stages: data access, SAR pre-processing, patch extraction, feature extraction, unsupervised clustering, supervised classification, rollup mapping, and then the Nansen sea ice drift integration. First, I mount the Google Drive using the following code. This lets me save downloaded Sentinel-1 data, figures, and results directly into my project folder. Next, I import the main Python packages. I use OS and glob for file handling, NumPy and pandas for numerical processing and data frames, matplotlib for plotting, and rust.io for loading Sentinel-1 TIFF files. I also use ski-image for patch extraction and ski-learn for k-means, PCA, and random forest classification. The main coding section is the Copernicus Dataspace API. I define a function as follows, which logs into Copernicus and uses my username and password and returns an access token. This token is needed to query and download Sentinel-1 products. I then define the query Sentinel-1 data using that function. This function takes a start date and end date, polygon, and token. Inside the function, I build an OData query that searches for the Sentinel-1 GRD products intersecting my Nares Strait polygon. The polygon I use focuses on the northern Nares Strait and the Robeson Channel region, given by the one starting with -7180. This area was selected because it captures the region where ice arch-associated sea ice conditions are important. The next function is download product. This takes a product ID and file name from the query results and downloads the sentinel1.safe.zip product into my Google Drive project folder. After querying the data, I search for products from January 2020 and August 2020. January represents a winter ice arch associated regime, and August represents a summer no arch or mobile ice arch regime. The code downloads one Sentinel-1 product from each period and unzips the files. Once the products are downloaded and unzipped, I search for all of the Sentinel-1.tiff measurement files using glob.glob. Each Sentinel-1 product contains a different polarization band. I filter the files to keep only the HH polarization using the following code. I use HH because it is commonly used for sea ice SAR analysis and it is sensitive to ice arch, roughness, deformation, and surface texture. I then split the HH files into January and August groups. The January file is assigned to ice arch files, and then the August file is associated to no ice arch files. These lists are later used to create the labeled machine learning dataset. The next stage is SAR loading and normalization. I define a function called load_SAR, which opens the Sentinel-1 TIFF using rust.io and reads the first band into a NumPy array. I then use normalize SAR. This function replaces individual invalid values, clips the image using the 2nd and 98th percentiles, and rescales the data between 0 and 1. This is important because raw SAR data can contain very bright outliers caused by strong radar scattering from rough ice, land, or other surfaces. For visualization, I also define load SAR preview, which loads a downsampled version of the Sentinel-1 image. This is important because the Sentinel-1 scenes are very large and can crash collab if plotted at full resolution. The next major step is patch extraction. Instead of classifying the whole SAR image at once, I divide the image into 64 by 64 pixel patches. I set this using the following code. Then I extract patches. This function uses view as windows to move across the SAR image and extract 64 by 64 windows. For each patch, I store both the patch itself and the row and column position in the original image. The position is important later because it allows me to map predictions back into the image space using the rollout stage. After patch extraction, I define isGoodPatch. This filters out the patches that are mostly empty or too uniform. It removes patches with very low mean brightness or very low standard deviation. This is important because full Sentinel-1 swaths may contain black edges, low information areas, or uniform regions. The next stage is feature extraction. I use a function called extract features. For each patch, it computes several statistical and texture features, including mean, SDD, min, max, range. The mean measures average backscatter. The standard deviation measures texture and variability. The range measures contrast. The Sobel features measures the edge strength, which is useful for identifying fractures, leads, ridges, and deformation structures. Entropy measures texture complexity, which is important for distinguishing consolidated ice from fragmented ice or open water. Then I define build dataset. This is one of the most important functions in the project. It loops through each SAR image file, loads and normalizes the image, extracts patches, filters bad patches, extracts features, and stores everything in a pandas data frame. After running the next code, the January patches are now labeled as Ice Arch, and the August patches are labeled as No Ice Arch. And once they are combined, this creates the final machine learning dataset. In my current run, the data frame contains 9,594 patches with 6,277 Ice Arch associated patches and 3,000 No Ice associated patches. The first machine learning method I apply is k-means clustering. I define the features columns, extract them into X, and then standardize them. This is important because features such as entropy and mean backscatter have different local ranges. Then I run k-means equals and clusters equals. This is the unsupervised part of the project. K-means does not see the labels, only sees the SAR texture features values and patches them together. I then add the cluster frames back into the data frame. I then plot the points by k-means cluster. This shows whether they naturally separate into groups. After the unsupervised analysis, I run the supervised random forest classifier. I use the same texture features as input and then label them. The random forest learns which combinations of texture features distinguishes Ice Arch and No Ice Arch associated patches. I then predict on the test set. The current model achieves around 99% accuracy with high precision for both classes. In this video, I would like to make clear that this does not mean the model directly detects the geometric Ice Arch. Instead, it means the model can distinguish SAR texture regimes associated with winter Ice Arch and no Ice Arch fragmented ice. I also compute feature importance from the random forest. This shows the variables which are most important for classification. Next, I create the rollout maps where the model is spatially applied on the SAR image. This creates the prediction map, takes the image, a trained model, and the scalar. I also extend the clustering to the full k-means using the following code, k-means4. This allows me to explore more detailed surface type regimes. After inspecting example patches from each cluster, I manually interpret the clusters as possible classes such as open water, land or coast, consolidated ice, and fragmented ice. The next step is important because unsupervised learning does not automatically have physical names. The interpretation comes from looking at the example patches and feature summaries. Finally, I begin integrating Nansen CI Drift. I install the CI Drift package and use Nansen functions such as getN, feature tracking, and pattern matching. The aim is to retrieve drift vectors from pairs of Sentinel-1 images and compare these drift products with the SAR texture regimes identified by the machine learning workflow. This integration is important because it gives the classification of physical interpretation. If ice arch associated star textures correspond to more consolidated ice, then they should be associated with lower or more constrained drift. If no ice textures correspond to fragmented ice, they should show higher or more variable drift. Overall, the code starts with Sentinel-1 data access, moves through the pre-processing, patch-based feature extraction, applies both unsupervised and supervised machine learning, creating a spatial rollout maps, and begins integrating sea ice drift retrieval for both physical interpretation.